In this video, I'm going to explain about continuity equation of current. Let us write an equation to show the continuous flow of current. As we all know, current is nothing but rate of flow of charges. I is equal to dq by dt. Current has the dimension of amperes. So current includes the flow of charges, the movement of charges or change of charge at a point from time to time. It's coulomb per meter. So charges produce current. This continuity equation of current is based on the conservation principle of charge. Conservation principle of charge. This is similar to conservation principle of energy, according to which energy neither be created nor be destroyed. Similarly, according to conservation principle, charges can be neither created nor destroyed. Charges can be neither created nor destroyed. Many times in literature, we can find statements saying that the charges are created. That means the charges which were attached to the nucleus of an atom are brought out by applying energy. That means they become free. Charges are always created in pair, positive and negative charges. Then we say charges are created, but charges were there. They were in the valence band. But afterwards, due to the applied energy, they become free. Then we say charges are created, but they have changed the form. Similarly, charges, sometimes we say they are destroyed or they are lost. But actually, they undergo recombination. So negative charges recombine with positive charges and get attached to some atom. So charges keep changing. Atoms are changing forms, changing nature, changing their properties, but they're neither created nor destroyed. So if you have charges in a place, and if these charges are not at all changing with respect to time, then we say there is no current. And if these charges are decreasing from time to time, then we say that some charges have gone out. They have flow out. Then we can say that there is some current due to these charges moving out of that point. Similarly, when the charges are increasing in number from time to time at a point or on a surface or on a line or on a wire, whatever it is, if they are increasing in number from time to time, then we say charges are flowing in to the point. That means we can say that current is flowing in due to the flow of the charges into the point. Then the charges at that point keep on increasing with respect to time. So keeping this concept in mind, we can define continuity equation of current. So for this, let us consider a closed surface enclosing a charge distribution. Let us start with a closed surface. Consider a closed surface. Let's say S, closed surface S, enclosing a charge distribution enclosing a charge distribution. So this charge distribution may be a volume charge distribution or whatever it is. Just for the sake of explanation, let us assume volume charge distribution of density rho v coulomb per meter cube. So now I have assumed a closed surface S. Closed surface S. And as I said, we can think of a charge distribution present within the surface and let rho v be the volume charge density of the charge distribution within the closed surface. This is the volume charge. Now, if these charges are permitted to pass through this closed surface to the outside environment, then we can say there is a current flow. That means if these charges are capable of moving out of this volume through the closed surface, then we can say that there is a current flow. And this current is denoted by I. We can make this statement about it. If the charges are moving out of the volume through the closed surface, S. The charges are moving out of the volume through the closed surface S. Then we can say current is flowing. We can say current is flowing. And this current is given by the equation I is equal to surface integral of J dot ds. I'm including the circle or integral sign to indicate the presence of closed surface. Yes. So what is J here? J is the current density. It's a vector in ampere per meter square. It is the current density. The density decides the amount of current flow. Current density on the surface. Current density on the surface. Current density may not be same at every point on the surface. That's why it is included within the integral sign. Current density may change from point to point. The total current I is given by the closed surface integral of J. Closed surface integral of J. Dot indicates that the current is flowing normally through the surface. That means if the surface S is having some direction, then obviously the current is assumed to be flowing perpendicular to the surface. If the current is not flowing perpendicular to the surface, if the current is trying to flow, that is, if J is trying to flow in this direction, then this angle of J with respect to the normal direction of the surface is considered. And to take care of this concept, dot is introduced into the product. The dot will include cos theta. So when theta is 0, so both the directions become same, then cos 0 is 1. So that gives us maximum current flow. That means the amount of current flow through the closed surface not only depends upon the surface area and the current density on that surface, but also the direction in which the current is flowing. The charges are moving out of the surface. So that's why the dot product. So dot ds indicates that normal component of current that is flowing out of the surface. That means if this is the surface, yes, and the current density J is acting in this direction, this J is not in perpendicular direction or parallel to the surface, then to understand the amount of current passing through the surface, we split this J into two components. One is perpendicular to the surface, another one is tangential to the surface or parallel to the surface. So J is split into two components, that is Jn normal component and Jt tangential component. Jt will not pass through the surface, but Jn will be passing through the surface. So Jn is given by J cos theta. J cos theta. This J cos theta is present in this equation in the form of J dot, and ds is the area. So this equation will take care of the direction. So we have explained, or we have understood the amount of current passing through a closed surface. Now, according to conservation principle of charge, when the current is flowing out of the closed surface, the amount of charge enclosed by the surface decreases with respect to time, because current is change of charge or increase of charge going out of the surface from time to time, then this is compensated by the equal amount of decrease of charge within the surface, right? So we can make a statement out of this one. So the current flow is compensated. The current flow is compensated by the amount of charge decrease within the surface. This is the qualitative statement. Current is flowing out means charges are moving out. Current means rate of flow of charge. Rate of flow, not only charge, the rate of flow of charge with respect to time. If current is the rate of flow of charges with respect to time, then inside the surface also it is compensated, should be compensated by the rate of decrease of charge. The rate of decrease of charge. That means the current flow can also be indicated as I is equal to minus dqi by dt. So the current which was given by surface integral of J measured on the closed surface is also given by the rate of decrease of charge inside the closed surface. Qi stands for charge inside the closed surface. So combining these two equations, we can write that I, the current, has two possible representations. One is the surface integral of J with its normal component. Another one is time rate of decrease of charge within the closed surface. This is a very useful equation, and we can call this the continuity equation of current. That means when the current is continuously flowing out of the closed surface, the charge within the surface also continuously decreases with respect to time. Let us label this equation as 1. So this forms the integral form of continuity equation. So the equation 1 is the integral form of the continuity equation. Integral form of the continuity equation of current. Integral form of continuity equation of current. Integral form is the equation which is applicable to a surface, or a volume, or a line, whatever it is, but not to a point. Now let us. If the charge distribution is a volume charge of density rho v, then we can modify the equation 1 to another useful form. Let us proceed in this way. If rho v is the volume charge density, rho v is the volume charge density of the charge. Volume charge density of the charge. Which charge? Charge within the surface, within the closed surface. Then let us introduce the charge density into our equation 1. Then if you know the volume charge density, then what happens? You can find the total charge inside the surface by the volume integral or triple integral of rho v. So we know this expression. This is going to be in coulombs, where rho v is charge density in coulomb per meter cube. dV volume is in meter cube. So total integration gives us total charge in coulombs. Now I would like to introduce this QI into equation 1, the continuity equation 1. Let me call this equation 2. So I would like to introduce using equation 2 in equation 1. We get some useful representation. That is, so the equation 1 is closed surface integral of J, that is equal to, the right side is minus dqi by dt, that is d by dt, differentiation of qi. Now the qi is the triple integral of rho v dv, volume integration. But here d by dt, that means the variation with respect to time is happening only with respect to rho v. That means within the surface only charge changes from time to time, but the volume does not change from time to time. We have taken a fixed closed surface which always encloses a fixed volume. So dV does not change with respect to time. What is changing with respect to time is only rho v, the volume charge. So that's why it is advisable to include d by dt to rho v, not to dv. So in my next step, I would like to take out the integral from rho v to combine rho v with dou by dou t dv. In this case, I would like to make two things clear. One is this differentiation and integrations are interchangeable because differentiation is with respect to the variable time, whereas the integration is with respect to volume, the space. Space and time are independent of each other. The space volume doesn't change from time to time. So volume, time, both are independent. So integration and differentiations do not get cancelled because of the different variables. Since they are independent of each other, integration and differentiation can be interchanged. So I have taken out integral sign and taken in the differential. And d by dt now becomes dou by dou t because when I wrote d by dt first time, we are differentiating only charge. The charge was changing only with respect to time. So it was d by dt. But now when I introduce the concept of volume charge, the charge not only changes from time to time, but also changes from point to point. This is being a volume charge distribution under consideration. The charge density may change from point to point. So some point may be more dense and some point less dense. So now the charge is depending upon not only with the time, but also with the space variables like x, y, z. So because of that, partial derivatives are introduced. So now, finally, we got integrals on both the sides. This equation is the complete representation of continuity equation in integral form. But only thing we have assumed here volume charge distribution. This is a more meaningful integral form. Because we have included complete space and time on both the sides. Integral form of continuity equation. Okay. This continuity equation is applicable to a closed surface enclosing some volume charge distribution. But we can modify this continuity equation into a differential form or a point form, which is applicable to a specific point or a very smaller volume. Instead of a larger volume enclosed by a closed surface, we can reduce or we can shrink the volume within the closed surface to such a smaller value where the small volume can be assumed as a point. So then the equation becomes a point form. So now I would like to give you the point form or differential form of the continuity equation. This is very useful in electromagnetics because most of the mathematical interpretations or mathematical analysis happen at point level. So instead of discussing the properties or characteristics of a particular electrical quantity or a space, we prefer to explain or analyze something at a particular point. This gives us more information than the integral form. So my next step is to remove these integrations and then convert them to a differential version of the continuity equation. So for that, what I would like to do is, I would like to convert any one integrals such that both the sides will be having a similar integrals. See, if you look at this one now, equation 3, the left side is closed surface integration, right side is volume integration. So we cannot cancel them to remove them, but we can convert this closed surface integral to volume integration, or volume integration to closed surface integration using appropriate theorems or laws. Right. If you observe the left hand side of the equation 3 carefully, this resembles one side of divergence theorem. Let me put an equation for divergence theorem in terms of vector j, then we will understand it easily. Let us consider the divergence theorem. Divergence theorem is a mathematical theorem. The divergence theorem in J. I'm going to take J vector to define the divergence theorem, because divergence theorem is a mathematical theorem which is applicable to any vector which has partial derivatives. So J being current, it is capable of spreading in all the directions with the different rates. So that's why J can satisfy divergence theorem, and it is given by closed surface integral of J is equal to volume integral of divergence of J. This is the divergence theorem. This is divergence theorem. One side, it is the closed surface integral of the normal component of a vector, and other side, the volume integration of divergence of the same vector. Now I would like to label this as equation 4. Now I would like to use this equation 4 into equation 3 for some conversion. If you observe here, the left hand side of equation 3, the left hand side of equation 4 are similar. Therefore, I would like to replace this left hand side of equation 3 from the volume integral of equation 4, so that both sides I will be having volume integrals, and then I can simplify it further. From equations 3 and 4, we get a very useful equation, that is volume integral of divergence of J. That is equal to, that is our regular volume integral of dou rho v by dou t dv. This is what the equation you got from the combination of equations 3 and 4. Now, this equation is applicable to a volume V enclosed by a closed surface. If I assume myself a very smaller volume, then also this equation is applicable, because continuity equation of current is applicable to any volume enclosed by a surface. So that's why this equation should also be applicable to an incremental volume or a smaller volume. So I can proceed in this way. The above equation is also applicable. The above equation is also applicable to an incremental volume, a smaller volume, a very smaller volume. an incremental volume, let us say delta V. Then I can write that above equation as divergence of J, divergence of J into delta V. Integration of triple integral of dV gives total volume V. Now I remove the triple integral dV by smaller volume delta V. No integration required, volume being a small, no integration required. Now the right side becomes dou rho V by dou T into delta V. So this is the continuity equation applicable to an incremental volume. Now since the volume definition on the left hand side and right hand side is same, so we can cancel them to get the final relation, that is del dot J is equal to minus dou rho V by dou T. Now this equation is applicable to any point described by a smaller volume. What volume? Differential volume, not even incremental. It's a differential volume. Incremental volume is a smaller volume. Differential volume is even smaller. That is dV, and this flow is delta V. So dV, the differential volume is so small that could be assumed as a single point. Hence, this equation is called by name point form of continuity equation. So this equation is the point form, or differential form. As you all know that point form, differential forms are applicable to points in the space. Point form of the continuity equation. The continuity equation. So this gives two different equations for continuity of current. One is point form applicable to a point, another one is integral form applicable to a closed surface. Now we can explain this point form of continuity equation to give physical interpretation of the continuity equation. So the physical interpretation or physical significance of the continuity equation is easily understood. Physical significance or interpretation is possible using this point form. Look at this part, that is left hand side of this point form. That is del dot J. Del dot, we know that it is the divergence. Del dot represents the operation, mathematical operation, divergence. The divergence of J. J, you know what J is? J is the current density. J is the current density. To take up separately, J is the current density in terms of ampere per meter square, current by area. Whereas del dot, being the divergence, has a unit of 1 by meter, or inverse of the meter, per meter. Okay, because del has an expansion of dou by dou x x. So dou represents change. Dou x is the change in distance. So denominator is the distance. So it has the dimension of meter. So totally del dot J has the dimension of ampere per meter cube. That means current by volume, current per unit volume. So del dot J mathematically represents current per unit volume. But physically, it signifies the divergence of current per unit volume. If you forget about meter cube for time being, you will be having amperes. So delta J represents the divergence of current. When you include meter cube, it represents divergence of current per unit volume at a point. So the physical significance of or physical interpretation of physical relevance of the left-hand side of the continuity equation is the current diverging from a point. That means if you have a point here, the current going out, diverging, opposite of convergence, the current diverging from a point is equal to, see what happens by the right hand side. Right hand side, dou by dou t, change of something with respect to time, minus dou by dou t, change means decrease of something with respect to time. The something is rho v. What is the dimension of rho v? The dimension of rho v is coulomb per meter cube. That means charge per unit volume. So dou by dou t says that rate of increase of charge per unit time per meter cube unit volume. Now if you introduce minus, this says that the rate of decrease of charge per unit volume per unit time. So you can say that one, the time rate of decrease, instead of per unit time, you can say the time rate of decrease of charge per unit volume at that point. That means if this point is having a volume charge of density rho v, then it represents rate of decrease of charge per unit volume at this point. So based on this discussion, I would like to give the physical significance of the equation, that is del dot J is equal to minus dou rho v by dou t. So this equation can be explained as this way. The current diverging from a point per unit volume. You know that this word per unit volume come from the dimension per meter cube. Current diverging means del dot. Current means the J. The current diverging from a point per unit volume is equal to, that means the current going out of a volume from a point is always equal to the right side now, right hand side of the equation, the time rate of dou by dou t, rate of decrease, minus sign now, the time rate of decrease of rho v, charge. But actually rho v is a charge per unit volume. That's why rate of decrease of charge per unit volume. How much volume? At the point. That means the unit volume is differential volume, which represents the point. This gives the physical significance of the continuity equation of current. The current diverging from a point, that means current going after a point per unit volume, is always equal to time rate of decrease of charge per unit volume. That means the amount of outflow of the current at from any point is equal to the speed of decrease of the charge, not the charge decreasing, the speed, the rate of decrease of the charge at that point. So if the charges are decreasing very fast, then more current is flowing. More current means the rate of decrease speed is very high. This one. So based on integral form also, we can make the statement of the continuity equation. So it is always best to make the statement of any law or any theorem or any equation from its integral form rather than a point form. So if you recall, the integral form of the continuity equation, that is closed surface integral of J is equal to minus dqi by dt. So this equation gives us the statement, mathematical statement of the continuity equation. So let us analyze the continuity equation in integral form in the same manner as we did the point form. Let us now start with the J. J is the current per meter squared, current by area. Similarly, ds is the area, that is nothing but meter squared. So J into ds will give us current. So this is the current. Dot indicates that we are taking normal component of current. J dot ds is equivalent to Jn into ds. Jn stands for normal component. If at all, if the current has to pass through the surface, it has to pass normally. The tangential parallel component, parallel flow of current to the surface will not pass through the surface. So dot ds can be declared as normal component of current flowing through the surface. J means current after multiplying with the ds. Integration means total. Okay. So anyhow, we shall make now the statement on the left hand side as the integral of, we are integrating, integral of what? Normal component of current. We are not integrating the total current. We are not considering the every complete current as the current passing through. Some current may be staying inside the surface itself. It may not be completely flowing out. The current flowing out is taken as normal component of the current. So that's why the integral of normal component of current over the closed surface or over a closed surface, yes. That makes the left hand side. Integration sign is there. So integral dot ds means normal component of what? Current J. The integral of normal component of current. We don't say current density because it is the product of J into ds. So that's why the integral of normal component of current over a closed surface, yes, is equal to time rate of decrease of charge inside that closed surface. Inside that closed surface. So let us write the statement now. The integral of normal component of current over a closed surface S. Let us call it S, is equal to what? Time. Otherwise, negative sign also we shall include here itself. Is equal to negative time rate of. Since I already defined negative sign, I don't say decrease. Say time rate of change of. Time rate of change of charge. Time rate of change of charge. Which charge? Enclosed by the closed surface. Surface is enclosing the charge. Charge enclosed by the closed surface. Say yes. This makes the statement, mathematical statement of the continuity equation of current. So according to mathematics, The integral of normal component of current over a closed surface. That means the normal component of current that is passing out of the closed surface. Integral means total sum is always equal to time rate of decrease of charge within the volume. So this makes the statement mathematical, and the previous one, that is from the point from what we declared, is the physical interpretation. So mathematical interpretation given by integral form, physical interpretation is given by point form. This completes the continuity equation of current. Thank you.